Hello everyone and welcome to part 2 of this week's lecture. In part 1 we looked at different definitions and concepts related with fluid flow, and we also saw that how we can use the technique of fluid visualization or streamlines to actually look at how the different layers or particles of a fluid flow in a system. So for example, if you have this particle here and you in time this particle moves, for example, to this point and to this point. So by joining these particles or their tangent velocity vectors, we can create what we call a streamline. So this streamline is in its simplicity is a visualization of how different layers of a fluid flow over a length scale. Okay, and we are going to use this concept in this part 2 here, where we are going to look at different flow regimes and how we can actually characterize these flow regimes. Okay, so before we go into more technical definition of these flow regimes, let's look at it based on a routine observation that you might have this as yourself. So for example, if you open the tap just a little, you see that there is a jet coming out of this faucet. And if you have opened the tap just a little, you will notice that the tap is much more uniform. The jet is much more uniform, and as such, we can represent different layers of these fluids or different particles of these fluids using streamlines. And these arrows are the streamlines that shows that there is a uniform velocity and there is not so much disturbance in this jet. Okay. While if you increase the tap or open the tap a bit more, you increase the flow, and the jet starts to get a periodic wavy structure. And if you look at the streamlines, if we visualize the streamlines, we can see that the streamlines also show that there is at some points there is a decrease in velocity. As I said in the previous lecture, if the streamlines are closer together, it means there is a increase of velocity, and if they are further apart, it means that there is a decrease in velocity. So you have regions where you have decrease and increase of velocity, and that creates some kind of disorder. Okay, and then you have the extreme case if you open this tap fully and you have very high velocity of jet coming out of this faucet. So you see that the water is quite disordered, and you have much more randomness in its structure. So for example, if you try to again represent it with help of streamline, so you can see there is a lot of intermingling or mixing of these fluid-like vectors here, for example, and that shows that the velocity is changing at almost every point in this fluid, and there is much more disorder. Okay, so we can characterize these three systems here. We call this system laminar fluid, where we have much more straight streamlines without any intermixing. And then we have the other extreme where we have completely disordered streamlines, and you have a lot of intermixing between the fluid particles, and that's what we call turbulent flow. Okay, and in between these two extremes, what we have this region that is called a transition region. For example, if you are transitioning from laminar flow to turbulent flow by increasing velocity, or the other way around. Okay, and this concept of turbulent flow, for example, it was reported by Leonardo da Vinci, and he sketched this his very famous turbulence sketch almost 500 years ago. And in fact, Da Vinci was the first person to use the concept of turbulence to show how the particles or the fluid elements are randomly mixed in a turbulent system. Okay, so this is a very simple way of explaining what is laminar flow and turbulent flow and a transition flow. Now let's try to understand it in more technical definition. So these flows were first observed by Reynolds, and he created a very famous experiment to characterize these flows in different regimes. And his apparatus looked like something like this. So he had a glass tube where we can very carefully control the velocity or the flow rate of the fluid in this glass tube. Okay. And he had another system where actually he could actually introduce dye of a different color at the center of this bigger glass tube. Okay. And so he could control the flow rate of the liquid flowing around the dye. Okay. So by doing that, he observed some patterns, and that's what I'm going to show you in the video here. So let me try to play it. So for example, here in this figure, the white portion is actually the water flowing in the tube. The darker portion, darker green portion is the dye filament. And then at the bottom, you again have the water because it's a tube, okay? So let's see what happens. So at this point, the velocity is much low, and you can see that you don't really observe anything, but actually water is flowing in this channel. And if you increase the velocity of this fluid, outside fluid, you see you start to get this disturbance just like the faucet as I explained, okay? So when you increase the velocity higher and higher, you get this disturbance, and now the liquid is going from a more structured flow towards turbulent flow. So at the moment we have transition region, and then if you increase the velocity of the outer fluid a lot, you have a complete disturbance or intermixing of different layers of fluid, and that's what we call turbulence. Okay. And here you can see we actually at University of Manchester they recreated this Reynolds experiment, and actually Reynolds was a professor of engineering at University of Manchester in 1880s. So this is still here. You can have a look at it if you want. This is what I showed you, that here you have the glass tube and inside you have this dye. And if you have velocity uz that is relatively low, you can actually the things will flow in a straight line without any intermixing. It means that the different layers will just flow adjacent to each other without any mixing. While you increase the velocity, you start to get a deviation in the velocity in the y direction, and that is the reason why you have this pattern of flow. And if you have very high velocity of this outer fluid, you get different components of velocity, ux, uy, uz. It means that you have three-dimensional flow inside, and that is why you have a complete disorder inside and a complete mixing. Okay. So Reynolds actually, in addition to doing these experiments, he also studied these systems for a range of different velocities. And he also tried to understand how different fluids, for example, if you're talking about water, honey, or other fluids like gasoline, kerosene, and how they play a role in terms of the flow pattern or initiation. And also he looked at different pipe diameters, that if by increasing or decreasing, can you actually change the startup of this disorder, okay, or the transition from laminar to turbulent flow. So as I said, that for the case of laminar flow, we can define it as is a situation or is when the fluid layers flow adjacent to each other without interfering and without intermixing. Okay, and we have these vectors, for example, represent the velocity vectors. So the velocity is maximum at the center, and as you go towards the wall of the pipe or the channel, the velocity starts to decrease. The reason being that at the wall you have the maximum friction between the wall and the water layer itself, okay? And that is why at the wall we normally say that the velocity is actually zero, and that's what we call non-slip condition. And as you move away from the wall, you still have the friction between the layers, and that friction between the layers is what we call viscosity, okay? So each layer away from the center is at higher velocity compared to the layer that is next to the wall. Okay. So at the center, you have the maximum velocity because you have the least effect of the wall, and also you have the viscous forces are minimum in the center. Okay. And the fluid velocity is a function of distance from the pipe center line. As I said, that away from the wall, you have at the center you have the maximum velocity, but as you go towards the wall, the velocity becomes zero. And we can by using this concept, we can or using some mathematics, we can actually develop this velocity profile. That is a velocity profile in a circular pipe. That is what we call parabolic velocity profile. And again, it shows a similar thing, that at the wall you have zero velocity, and as you go away from the wall towards the center, you have the maximum velocity. Okay, and we will look at this how we can develop these velocity profiles in part 4 of this lecture. Then we have the turbulent flow, in which the fluid elements are much more irregular, and there is a lot of cross mixing, and occurs at high velocity. Hence, okay, so this turbulent flow, as I explained in the previous slides, that it happens mostly when you have a very high velocity, and because of high velocity you have high momentum, because momentum is velocity times mass. So if your velocity is high, you have high momentum, and as such you have high inertia. And inertia is a property, for example, that doesn't want to change the system. For example, if the system is moving, it doesn't want to stop, and it wants to just keep moving. Okay, so that is what we call inertia. And these inertial forces are more dominant than viscous forces. So viscous forces are the forces due to viscosity between the different layers. And because of this, because the velocity is quite high, the inertial forces, or the forces due to the velocity of the fluid, become more dominant than viscous forces, and as such you have much more mixing between the layers. Okay, so high shear stress at wall and steep velocity gradient near the wall. So when you are in turbulent flow, you have a more flattened velocity profile, and the reason being that in the middle you have much more mixing, and as such you have much lower effect due to viscosity compared to the parabolic velocity profile that was something like this. Okay, so in the middle you have much higher velocity compared to turbulent flow, but in turbulent flow the velocity of this whole section is more or less equal, or relatively equal, because of this a lot of intermixing. And then you have this last portion that very much look like the parabolic profile of laminar flow. At the wall, again, you have no velocity because of the non-slip condition, and then you have a very steep increase in velocity as you go slightly away from the wall because of this turbulence or intermixing. Okay, so the velocity profiles, as I showed you in the previous slide as well, depends on the distance from the pipe center line, and is known as a velocity profile, how the fluid is actually, what are the velocity of different fluid layers at different points in the radius, for example. Okay, and these velocity profiles are really important because it helps us to understand how much flow rate you are going to get in a pipeline, and they also help us to understand what are the effect of for example, viscosity on the pressure drop. Okay, so we will see all this in the next two parts of this lecture. Okay, so how we determine the flow regimes. Okay, and so Reynolds come up with a number, or he observed this situation, that how the velocity is affecting this turbulent to laminar to turbulent transition, how the viscosity is playing a role. So he came up with this number, a dimensionless number, and that is what we call a Reynolds number, and that is actually equal to diameter of the pipe times velocity times density divided by the viscosity. Okay, so these are the factors that tells you that how the and when the fluid is going to transform from laminar to turbulent flow. Okay, and this number is dimensionless number because if you use, for example, for diameter, you use the units of meter. U is meter per second. Rho is kilograms per cubic meter. Density, you can see here on the slide, we discussed in the first lecture, is a ratio of stress over strain rate. And if you calculate the units from this formulation, the viscosity has units of kilogram per meter per second. And if you feed all these units in this equation, Reynolds number come with a unitless number. Okay, these numbers are very important in chemical engineering because you don't have to worry about the units of the system. Okay, you just know the number, and these numbers dictate different parameters of chemical engineering process. There are a range of numbers, and chemical engineers love these numbers, so you will see a lot of numbers over your 4 years of education. Schmidt number, Froude number, and other more important numbers as well. So yeah, flow regime. So as I said that how we can use this number. So for flow in pipes, okay, and these different numbers actually slightly depend on the geometry as well. Okay, so Reynolds number for a fluid in a pipe, if your Reynolds number comes out below 2100, your system will be in laminar flow. Okay, that is shown here. For example, you can see that there is laminar flow, and if you look even at the layers, somehow you can see these layers of the liquid, they are flowing without any intermixing. Okay, so very good demonstration of this laminar flow here. While if your number is greater than 4000, you are in turbulent flow. Okay, and here you can see this video here that in the first case you have Reynolds number is 1600, so you can see there is much less intermixing. But as your Reynolds number increases from 1600 to almost 10,000, you can see that here in the last part you have much more turbulence compared to much more straight lines here compared to the complete disorder in the last section. Okay, and then in between these two numbers of 2100 and 4000, you have what we call a transition region, as I explained you in the previous slides. Okay, yes, so most unfortunately most process engineering applications are turbulent. But turbulent case, actually, we are still not able to analytically solve turbulence. Okay, so this is one of the biggest challenge of 21st century, is to actually develop system to solve turbulence analytically. We always have to use numerical methods. We cannot actually even solve turbulence using analytical methods. Okay. So another way of looking at Reynolds numbers is actually that it's a ratio of inertial forces to viscous forces. Okay, so if we look at again the definition of Reynolds number, that is that it's d times u times rho divided by viscosity. And as you can see that the viscosity or viscous forces are much more easy to understand, while we have here the inertial forces. And inertial forces depend on a few factors. So for example, we have the density of the fluid, we have the diameter of the system or of the pipe. So by fixing rho, we fix the nature of the fluid, and by fixing d, we actually fix the geometry of the fluid. Okay, so these two factors dictate the nature of the fluid and the nature of the geometry, or the geometry of the system. And then you have the middle property, that is velocity. That is actually so the higher the velocity, the more inertial forces you will have, because as I said in the previous slide, that it comes with this m times v, that is the uh, uh, momentum is equal to mass times velocity. So the more velocity you have, the more momentum you have, and as such, the more inertial forces you have. Okay, so it means that when the fluid is flowing, it just want to keep going and it doesn't want to stop, and that is what we call inertial forces. Okay, so that is all for this part, and in the next part we will look at again more details of viscosity and what are the implications of this viscosity on the flow systems. Thank you for your time.